All right, guys, welcome. It's 6:30, so let's get started. Welcome back from your break. So we are going to get started. Today is the first lecture, first week, semester. So this is the sign-in sheet. If you can please just sign in. All right, so today on the agenda, I'm going to go over the syllabus, go over, some of you have taken, the previous class with me, and some of you might be new, so I kind of need to get everyone to understand everything. So for some of you, I'm repeating some things, right? Um, so this is practical deep learning, right? The course. ITS 530, this usually follows ITS 520, although they are somewhat different. So it's some students take 530 and then 520. So, but that's fine. Um, this is a more advanced course than 520. This is a deep learning, as you can see, is in the name. Okay. All right. So we'll start with Brightspace. This is where I'll post all the links and everything. Uh, the syllabus is here and all the materials. So usually the way that the way that I do Brightspace is, so we'll go here. There's only one section this semester for 530, so you guys are 001. You click on that, and then I post everything in content, right? So you can click on content. I've already loaded a lot of the materials, but I'll be updating this as I usually do. So then you can click on table of contents here, right? And then you can see I have some of the modules loaded already. Essentially everything, all the materials are here. Sometimes these are just going to be links to code on my GitHub, or there might be some links to, materials, right? Papers, research papers, things like that. The first module is the surveys and the term project. So that's, I'll update this later, but this just gives you an idea of what we've done in the past. So some term projects, so you can take a look at that. But we'll modify it as we move through the semester. Then I have the admin folder. This is where the syllabus is. So we're going to cover the syllabus today in detail. Just get a feel for the topics, everything, the course description, grading, things like that. Then, of course, I usually have this module resources. This is where you can find a lot of the links that I'll be using in the class. So, for instance, I'm recording the video right now, and then usually the next day or so I'll post a video on YouTube, and this is the link to the YouTube channel, so you can just get the video recordings from there. Right? So you're still supposed to come to class. This is just meant to help you in case you miss something, or if you missed a class, like a snow day, something like that. This is the link to the repo. This repo is different from the 520 repo. So I'll click on it, and you'll see I kind of labeled it as, or named the repo Transfer Learning, but that's the one where all the materials are posted for the semester. Okay. So these two are really important, obviously. The YouTube videos and the GitHub. Website, I've put together some websites with information, and so where I have like descriptions of the different algorithms, things like that, so I'll make those available. But this would be a central repository for that. All right. And then, so that's resources. And then we just get into the first two modules, so Transfer Learning Intro and Hugging Face, Transformers, BERT. So that's going to be some of the first modules this semester. Today I'll just motivate, right, what transfer learning is and how it relates to deep learning. It is deep learning, just you have to think differently, right, about deep learning. So this course is going to cover algorithms in deep learning, that we write from scratch, as well as just using very high-level libraries that allow us to bring in deep learning algorithms that have been pre-trained by others, right? So if anything, we'll be fine-tuning. So if you remember in 520, we would train everything from scratch, right? So we would start with random weights. Here sometimes we will have pre-trained models, and sometimes we'll have random as well, random weights. All right. So yeah, so I'll go through these modules, but first, I'm just giving you the layout of Brightspace right now. So I don't do like week 1, week 2, week 3. Instead, I'm just going to name modules by the topic, so you can see that here. And so these are all the topics. All right, and we'll cover a few more possibly. All right, so now let's get into the syllabus. Just go through that, get that over with, and then after that, I just plan to do like a demo of things to come in the semester, some useful things that we can look at. All right, before I begin with the syllabus, are there any questions, I should say? No questions? Nobody has any questions? All right. All right. Okay, so let's formally go through this then. This is ITS 530. The official title is Practical Deep Learning. So, you know, that's a deep learning course, but it's supposed to be like more applied, I guess, something like that. All right, I'm Professor Calix. My office is Anderson 238. That's my number, my email. Office hours are going to be Mondays and Tuesdays from 1 to 2, or Wednesday 4 to 6, or otherwise by appointment. So you have to send me an email and we have to schedule it. Make sense? Yeah? All right, great. So this is spring 2026. All right, so let's go over this. This is the most important part of the syllabus, right? The course description. So practical deep learning, this course covers the theory and technologies related to deep learning. Right, so pretty much anything that is deep learning. For those of you that have taken a neural networks class, what is deep learning? Just you have an input layer, an output layer, and in between a hidden layer, so you just have more of those, more complex, right? So that's a very, broad description of the course. So there's a lot of topics that we can cover, and keep in mind that deep learning is evolving all the time, right? So right now, maybe there's an algorithm being invented or a technique or something, right? So there's JEPA right now, for instance. I don't know if you've heard of this from Jean LeCun. I don't even know how it works because I don't know if I can trust it yet, but that's a new thing on the radar. You see what I'm saying? So if time permits, we might look into that, but I just don't know if it's gonna be helpful or not, right? But it's a new, Jean LeCun left Meta recently, right? He was the director of AI. He's left it now, and he's got a new startup, and apparently it's all gonna be based on something called world models and JEPA. That's all I know about it. So this is how fast all of this moves. All right, but in the course, we're going to cover a lot of the algorithms, a lot of the foundations, right? Just related to deep learning. What are the new approaches to it right now? And then on your own later, as you move on, you'll have to learn some of these new algorithms by yourself. All right, so the course description, the course covers the theory and technologies related to deep learning. In particular, the course focuses on the following topics: neural networks and hidden layers, so anything that involves that. So that's very broad. There's a lot of algorithms, I could say stable diffusion, right, is neural network with hidden layers, right? So RNNs, LLMs, we covered LLMs already, if you remember, in 520. So that's not a topic I'll cover here, but I'll be covering a little bit more of the image-based approaches for sure. We started with GANs, if you remember. Here we're going to continue with that. We just did some very basic stuff. This will have more room to focus on these algorithms. All right, so the topics: neural networks and hidden layers. The next one, issues with designing deep neural networks. So here in this issues in designing deep neural networks, we're going to talk about transfer learning, right? So the key things that we have to consider, such as it's hard to pre-train a model, it's very expensive, but it's cheaper to borrow someone else's pre-trained model and then fine-tuning it, right? So that's so that topic is called transfer learning. I do have a Word document or a PDF, I think, with a write-up on transfer learning. So, we'll talk about that today. We'll just expand on convolutional neural networks and how they work all the way up to ResNets. So we'll talk about that. Recurrent neural networks, so that's sequential machine learning. So if you've ever heard of a term called time series analysis, time series data, right? So there's a lot of traditional methods for that, something called ARIMA, etc. Those are the classic methods. But you can also do time series with neural networks, with deep learning. The most basic approach is to do an RNN. So we'll cover that in terms of time series. Then GANs, so generative models, generative adversarial networks. So we'll talk about that in more detail. So that's image generation. So that's going to be one of your homework assignments, doing image generation with GANs, CGANs, and stable diffusion. So those are the algorithms. Then we have batch optimization, which is optimization ideas. Word embeddings, that just relates to anything that, language based we're going to create. And that in 520 we covered like GPTs. Here we're going to spend some time on BERT models. So that's going to be a little bit different. And you'll see how that has other applications actually for transfer learning. And then other special topics, different algorithms that might be available. Throughout all of this, the main theme will be transfer learning a little bit more than just training things from scratch. Okay? So that's the course description. Are there any questions? No? All right, so the course objectives, as I said, we'll do transfer learning. The great thing about, a more practical approach to deep learning, as the title of the course says, is that, we're going to be using more powerful models, right? So when it's definitely for image processing, image classification, you'll see the improvement, right? So between using a CNN that you train versus a ResNet 50, right, that has been trained by Google or something like that. It's a much more powerful system. All right, so anyway, so these are some of the more detailed descriptions of the topics, understanding of transfer learning with convolutional neural networks, and so on. Prereqs, so ITS 520 is or equivalent. So really, the way that we designed the class, initially we had 520 followed by 530. Over the years, some students take 530 first and then 520, so should be fine. You should know a little bit of programming, though, right? So this course does use Python extensively. But actually, I would say some of the code is actually easier, as you will see today, hopefully, because we use a lot of libraries. So we're going to use this concept of encapsulation, right? So if you remember in 520, we would write code in classes, right? And we would encapsulate models and things like that. Now imagine that someone has taken all of that from PyTorch and created libraries. And all they're doing is they're encapsulating all that code within their library. So now in 3 lines of code, we download a GPT, the tokenizer, and do some sentiment analysis. You know what I mean? So that's the approach here. But everything is still PyTorch in the background. It's still a deep neural network. It's just being more encapsulated. All right, so I'll demo that today. So knowledge of programming up to data structures, Python, and statistics is required. The course runs from 6:30 to 7:50, and then we'll take a 10-minute break, and then it'll go from 8 to 9:20. Okay, and so that's going to be the course. As far as the books, there's no required book, so you don't have to buy a book if you don't want to. For those of you that like reading books and you want to have one, this is probably a really good one. It's called Deep Learning by Ian Goodfellow. So, it's like a great book. It's got all the math background and everything for many of the algorithms. Just keep in mind, as I said, I don't know what edition they have currently, and it's going to be missing some algorithms because this field is advancing really quickly. And then I will provide all the other materials in the GitHub, or I'll provide like reading materials, etc. Again, some of the topics in more detail. All right, as far as the grading, there is a project, which is 20% of your grade. We'll decide somewhere in the middle of the semester what we're going to do for the term project. I have some thoughts on that. I would want for you guys to do some transfer learning there. So we'll see. Exams, that there's going to be 3 exams. That's 30% of your grade. So each exam is worth 10%. So this is currently week 1. So the first exam is on week 6. The second exam is on week 12, and then the third exam is on during finals week. Make sense? Yeah. And those are written exams, pretty easy, really. All right, and then as you can see, assignments, which could be labs or mini projects, everything here is going to be involved. That I can tell you that right now, because yes, the libraries help, but there's going to be a lot of files that you're bringing to use. Also, it's going to be large files, right? Large models. Remember that some of these things are going to be pre-trained with 2 million images, and it's going to be a ResNet 50 or something, which means it's 50 convolutional layers. So you can imagine how big that's going to get. So that is going to be one of the challenges. It's unfortunately one of the challenges of deep learning, right? The more powerful the model, the bigger it is, just the more space it takes, the more memory it needs. So yeah, get ready for that. We've used Colab in the past. We'll continue to use that today. I will demo, for those of you that may be new and don't know how to use Colab, I'll just start it and then we'll do some examples today. All right, assignments, as I said, we'll probably do a stable diffusion example, some kind of RNN, some transfer learning things. So it'll be different kinds of assignments. Okay. Any questions so far? All right. Let's see. Please read through these. These are just recommendations as far as attendance. As I said, you technically should come to class. The videos are just to help you out. It's not an online class. Now, with assignments, we'll be using Brightspace for submitting homework assignments. So the only thing there is please submit homework assignments on time. Otherwise, once the link closes, you're not able to submit anymore. Please don't send me homework assignments via email. Usually what I want is just a report, right? You can provide files and things like that, but it's really about answering whatever the question was or achieving the goal and having a report with screenshots and information. Usually I provide a lot of the code, so I don't need to see the code, right? We'll be using PyTorch, not TensorFlow, right? Especially because it builds up on what you learned from 520. But we will be using a lot of new libraries like FastAI, Transformers from Hugging Face, all the deep learning advanced libraries that are available. Okay. Yeah, read through everything, please. Here's a list of some of the topics. I think I did update this last week. So this is suggested, and this is what I'll try to follow. So week 1, introduction to deep learning and transfer learning. So what are those? What does that mean? The basic deep learning approach, right? Preparing your data for deep neural networks. Preparing data is going to be challenging now because we're using libraries, right? So libraries were designed by people. They made choices based on what they like. And so they have very strict formats for the data. And so we now have to learn how to format things in ways that they will fit into these libraries. So that's going to be part of the learning curve, as you will see. Building and evaluating deep neural networks. So that's one of the things that we're going to do. So how do we build from scratch, and also based on transfer learning, how do we build deep neural networks. I have here transfer learning for images. I actually think I'll cover transfer learning for images like in the second third of the semester, and I'll start with the language part in the first semester. So I just need to move these. But yes, these are topics that I'll cover: transfer learning for images, such as GANs, transfer learning for images, special topics such as stable diffusion, and of course, fast AI, which is a CNN, right? But it's a residual type of a CNN network. You will not, obviously, it doesn't make sense for you guys to build a ResNet from scratch, right? So we're talking about 50 convolutional layers, you know what I mean? So you wouldn't be able to train that anyway, right? Think about it. It would be impossible. And so instead, you probably won't see the architecture as much anymore, but you just know I have a ResNet and that's what I'm using. And you have to understand that inside, in PyTorch, it is actually 50 layers. So we'll see that. Then, as I noted here, exam 1 will be on week 6. Then you can see I kind of have these in the wrong order. So this is actually where we're going to start. So large language models and transformers, RNNs. So we'll cover RNNs in the next few weeks. Today I'll just start with inference. So essentially now we can do inference right off the bat. It's like, we don't have to train a model and then do inference. The libraries now give us the option to just bring in a model that's already pre-trained, and then we can just start using it. Okay? And so that's called usually inference. That's the inference part where you're just predicting. So that's what I'll do today. I'll start demoing, right, how we can use these libraries to start doing inference. Okay? And we'll start with large language models. So that means I'll probably bring in a BERT or a BART or a Roberta or all of these, right? They have these acronyms, but the underlying architecture is still a large language model. So it's a transformer. Okay? And I'll talk a little bit about the history and where those names are coming from. But yeah, so we'll do large language models. We'll cover RNNs a little later. We'll cover BERT, as I said, in this semester instead of GPTs. And that's actually, it fits nicely with transfer learning. So that's why I do it like this, because so the way that large language models are trained is that, what you guys did in 520 is you pre-trained it. But then after pre-training, you would do fine-tuning. And then after fine-tuning, you do something called reinforcement learning. So there's like 3 steps that are done. So we'll discuss all of that, right? Now, the reinforcement learning is, as the name implies, is where the model gets some reinforcement, so some feedback. And so we'll see that. So it's almost like, you have a large language model, you ask it a question, it gives you an answer, and then you, as a human, you would say, okay, give me 3 answers, and I can give you some feedback. So then you get 3 answers, and you say, I like this answer better than the other 2. And then the model uses that information to update the weights. So you're still updating the weights, whether you're doing pre-training, fine-tuning, or reinforcement learning. Do you see that? But it's just 3 different approaches. So pre-training is something that we've covered in 520, so here I'll just cover more of the fine-tuning steps and the reinforcement learning. So where does BERT come in? Well, BERT is another model, and what BERT does is it basically can be trained to do the feedback. So instead of a human doing the feedback, BERT can do the feedback. Do you see that? So we're going to give BERT, so you know how you can give a large language model a prompt and it gives you some text, right? So we can train a BERT to where we give it some text and all it provides is a score, a number between 0 and 1, such as saying this is a good answer or a bad answer. Do you see that? So that's one of the things that's going to be one of the first homework assignments, and we'll explore that concept. So BERTs, whereas in 520 we covered GPTs, here we're going to cover BERTs. Very similar, right? They're very similar in architecture, but it has a different kind of use. And this feedback use is actually a very powerful one that we're going to study. So for instance, in the past, students take a GPT-2, a pre-trained GPT-2, They give it a prompt and it gives an answer, right? And then they, the assignment is essentially to make that GPT-2 be funnier or be more like Shakespeare or be more like, I don't know, something else, right? And so students then, all they have to do is they have to get a BERT that takes text and it gives a score indicating, okay, this sounds like Shakespeare or not, or this sounds funny or not. You see that? And now you can use both of these models together. So the BERT provides feedback to the GPT and they work together so that eventually the text should become funnier just because of this feedback. So this is how they initially got ChatGPT to work. I know that there's been a lot of improvements from there, but that was one of the key breakthroughs that made ChatGPT work. Does that make sense, guys? So that's the idea. So again, a lot of complex things that we will discuss later, but that's how BERTs are going to fit in. And BERTs do have other applications, as we will see today, actually. But that's one of the things that we will do. And it relates to transfer learning. So that implies that we'll cover a little bit of reinforcement learning, and that's an area in the context of like large language models and and GPTs. All right, so large language models and transformers, designing deep learning algorithms. So that's quite broad, so we can cover many things. Large language models and transformers, special topics. Word embeddings, as I said. BERTs also are, if you think about it, and if you remember from 520, LLMs are just embedding machines, essentially, right? So you take an input in text, and you're transforming it, and you just get a vector with numbers, right? And that's called an embedding. And so we're just going to expand further on this idea, okay? Issues with optimization and deep learning, special topics, and so on. So that's, and then the final, there's going to be the project, of course, and then the final exam on finals week. Then as far as the syllabus, make sure to read this. This is the university emergency procedures, so make sure to read all of that, please. Yeah, and that's the syllabus. Any questions on the syllabus? No? All right, great. So that's kind of the end of like the administrative things. Let's just go back to the table of contents. Let's look at some of the topics that we'll be covering, and then we can just get started with today's topics. As I said, today is the first day, obviously, so it's more of just me showing you a few things. It shouldn't be anything too complicated, but we'll get to use Colab for anyone that hasn't used it. We'll talk about that, how that works, and get to look at some of the code, some of the libraries, etc. All right, so you can see this is kind of the order that I have for this semester. So, introduction to transfer learning. Hugging Face Transformers is really the key library that we look at here. Torch, obviously, for anything related to deep learning, right? So we're either so the way that you have to think about it is we're either building a deep learning model or we're using a deep learning model. And whenever we're using Hugging Face, we're using a very deep, very large, deep learning model. So you heard me say that we use GPT-2, and you might say, why GPT-2? Why not, I don't know, what is the latest one? GPT-4o or GPT 5.2, right? Or Claude or Anthropic. Well, the problem is that those, the more advanced the model is, the bigger it is. So if you can get 4o to run on your machine, go ahead and use that. But for a lot of the things, you'll give up and you'll probably just go back to GPT-2 because you can still do the assignment and it's going to run a little bit faster. So unfortunately, that's the challenge, right? Some of you that get like Colab Professional and use the Teslas or whatever, like some of you do sometimes, okay, maybe you can run a more powerful model. Does that make sense? So it's the same thing as before. We're still limited by the resources, and so yeah, that's going to affect your choice of model, right? But my demos are usually with GPT-2 because I know those will run. All right. Yeah, so as I was saying, the first few things we'll cover, that what we're going to cover today is this. So I'll give a quick introduction to this concept transfer learning, what it is. It's very easy actually to understand. We're always, whenever we're training, whether we're doing pre-training, fine-tuning, reinforcement learning, transfer learning, we're always updating the weights of the neural network, right? So all the layers in our deep learning model, they have all these values, the connections, right, the weights, and we're just updating them in some way. And reinforcement learning is certainly an elegant thing that I like to cover in this class. A lot of people like Karpathy say that is not an elegant solution. Like they say it's not the right solution for AI, even though it's so powerful, right? So a lot of people who study this field wish that there was something better, but that's what we have today. And I think it's really nice. All right, so this is the first module. So I provided I think this is the Vaswani paper. So you guys can start reading through it. And this is just attention is all you need. So this is the paper that first proposed the transformer, right? So just read through it. If you don't understand anything, let me know. But yeah, I'll provide we're not going to go over the algorithm again, as that's what we covered in 520. For those of you that haven't taken 520, just take 520 next semester and we'll cover it then. That doesn't affect you, but certainly read the paper as best as you can. All right. Hugging Face, this is an important link. So when I mentioned that we're going to be using the Transformers library, so that's a Python library called Transformers. It was developed by them, Hugging Face. Hugging Face, I believe, is like a startup at this point. It's a company, right? As a lot of things are. OpenAI is a company, right? All the developments that are happening in AI happen in companies, Google, etc. And this company created the library called Transformers. Is probably the most popular, transfer learning library. So we'll be using it for the course, and it's very, this is essentially a place where you can exchange models. So you can see that here. There's a link, you can click on that, and these are all the models. So you can literally create your own account here, right? And then, maybe deploy your own model. So like if you train something that you think is really good, you can make it available here. And then others can use it from the Transformers library, using the Transformers library. So usually companies like NVIDIA, you can see NVIDIA has their own account, and Meta and Google, and they also make their models available here. Remember, these are now deep learning models in PyTorch or whatever, but they have been pre-trained, maybe fine-tuned for some specific task, and then they're made available here. Got it? So, and there's going to be, as you can see here, the different tasks are like text generation, image to text. I mean, there's lots of things. There's lots of libraries. So you can do text, images. So there's a lot of options. Okay, but we'll start with this one. I do definitely have a few other options that we will cover later in the semester. There's models developed, in the United States, of course. There's models developed in France. There's models developed in China, right? So there's all kinds of models, all very powerful. DeepSeek, I don't know if you guys heard about that, like last year. So I do actually do a lecture just on that because it was so significant. So we'll discuss the implications of that. So yeah, but this is the library that we will be using, and you'll see me. So whenever I'm downloading a model, you'll see that it has some kind of a user, and then that will be followed by the model that we're using. So for instance, GPT-2 will be one of the models that I'll use for the demos in class, and today I'll actually download many models. Okay. So yeah, so Hugging Face is pretty important. And actually, some of the reading materials will be on the Hugging Face website because it has a lot of blog posts and explanations, and this company is at the cutting edge usually of deep learning. Okay. Let's go back here. And then, as I said, I'll get into this PDF in a little bit. And here, this is for today, this is my demo. So this is a link to my repo, which is going to have all the scripts that we're going to cover. So I have them in Jupyter here. So all these I, P, Y, and B, I'll be running them and explain how it works. And we'll go over that. So remember, today we're just doing inference. There will be no training of any kind. But, in the future, we're going to, in the next few lectures, we'll start to get into this idea of fine-tuning. And I realize there's a lot of new terminology, right? So that's what the PDF hopefully will help with, is it'll give us all these names. What does fine-tuning mean, and so on. All right, and then before we get into it, let's just look at a few of the other topics. So as you can see here, BERT, reward functions. So we'll talk about this extensively, how we can use a very deep neural network, right? A transformer-based deep neural network called the BERT, right? I'll provide this. There's a connection between all these names. So I have to explain how that works, but then it'll start to make sense. Like if you see a BERT, you know what they're talking about, or a GPT and so on. I'll cover agents, AI, just briefly. I'll show you how that, in terms of how to implement deep neural networks that actually do tasks. This is just another level of encapsulation, right? So we'll cover that at some point. Reinforcement learning through human feedback. So this is actually like the optimization part of this, right? So we have, remember that there were two functions in neural networks, if you remember, right? There was the inference function, which was the x times w plus b, if you remember that. And then there was the loss function, right, which was like your cross entropy or something like that, if you remember. So now we have a new type of a loss that we're going to be considering, and these are going to be the new losses based on reinforcement learning. Okay, so it's like an additional level of training that's going to happen. So we'll cover that. So I have reinforcement learning here, reinforcement learning through human feedbacks. DeepSeek we'll talk about, very deep neural network that was very important when it happened. It still is. Word embeddings, autoencoders, BERT, all of that, fine-tuning. Then, somewhere around here, the exam 1. Then we have sequence mining and RNNs, right? So we'll talk about that, like time series problems. RNNs can be used for language, but they have disadvantages. So usually now, RNNs, if you ask me what you would use them for, I would say time series. So that's like a more, ARIMA. A lot of people that do time series analysis are still kind of stuck in the old methods. So they still use like this thing called ARIMA or something else. But if you want to move it up to more modern approaches, then I would say RNNs are pretty good. No one has yet to apply a GPT to time series, right? So that's still something that I guess they're researching, but so far no one has been able to implement a GPT that can replace RNNs for time series, as far as I know, right? Okay, another important library that we will cover as it relates to images is FastAI. So FastAI can be used for language, but it is mainly for image processing. And I think you'll learn to appreciate that. It's a really nice library. So now you'll be able to solve many image related problems once you have FastAI. This works really well because you're using a pre-trained ResNet that was trained with like 3 million images. And so, it can detect whatever. You'll see they're really good. And so we'll use FastAI essentially to try to solve problems. So FastAI pre-trained image classifier with your data, so we'll do that. How to load your data, FastAI examples, and we'll do some foundations of computer vision with PyTorch and FastAI. We'll cover, as you can see here, art style transfer, so that's actually based on like GANs, and so we'll cover those algorithms of GANs and stable diffusion. So this is more of an image related section. Object detection also works really well. This is actually another library called YOLO, and there's this is used in industry. Like this is already so robust that companies use it for their applications for object detection of any kind of object. Works really well. And then yeah, and then the final exam, so, some algorithms here and there. Makes sense. So this just gives you an idea of some of the topics that we will cover. Obviously, we'll we'll get into the details. Any questions before we begin, guys? All right. So let's see. It is So we have time. So let's now get into the topic. So today, I'm gonna assume that all of you are new. So I'm gonna cover Colab just briefly, give you an idea of how to use it, and then after that, we're going to start using the Transformers library just to do some examples. Okay. So so how do you use, what is Colab, right? So Colab is an environment provided by Google, right, that allows you, it's like a Jupyter notebook. It allows you to run code. And it's an environment that gives you access to either a CPU, a GPU, or a TPU. Right, so that's really great, obviously, because as you guys know, training models, especially deep learning models, can take a long time, and so having a GPU is definitely an advantage. Okay, so how do we use Colab? So go here. I'm already signed in, by the way, so I have, you have to have a Gmail account, and then you get access. You create a new notebook. Oh yeah. The what? Are they going away? Oh, okay. Well, they're gonna give you other email. I mean, yeah, but you still need to have a university email. Yeah, so maybe you're switching platforms. Yeah, yeah, but I think, I mean, you're still gonna have your a school email. Mm, is really? So how will you prove that your students to get the? Oh, you can still prove. Okay, then yeah. So you'll just create a Gmail account then. Sorry, I didn't know that. Yeah, sorry, I didn't know that. Yeah. Well, let me know if you have problems, but try with just a personal account. I'm using a personal account, I think. So, all right. Anything else, guys? But yeah, so far Colab has worked really well. I've been testing this, and all the transfer learning examples seem to work with Colab. So I think it's, obviously if we start using really large models, we may start to run into some problems, but we'll have to wait to see. Okay. All right. So yeah, so this is Colab, right? So you sign in, you guys. So you create, you click on code and you create these little boxes, and then this is where you will run your code. So you type your code here and run it like this. All right, so for today, we don't need any files, but in the future, once we start adding files, one good approach is to use Google Drive. So you can put your files, and again, you'll have to use your personal Google Drive. I'm using my personal Google Drive. So you'll put your files on Google Drive, and then when we get to that point, I'll show you guys how to mount the Google Drive on Colab as one approach for running your data. Okay? Make sense? All right. So yeah, so that's kind of the Colab. It's pretty simple, I think. All right, so what we're going to do now is I'm just going to demo some examples, and then we'll do the PDF towards the end of class today. But I just want to show you, what you can do, right? So we're doing inference, remember. So usually in the past, usually in machine learning classes, you talk about the data, and then you think, okay, I'm going to build the architecture. I'm going to train the model, then I'm going to measure performance, and that's it, right? But this is more of a, as the name implies, practical. So a lot of it is problem solving, and transfer learning is really well designed for that, right? And so I'll show you today that we can just download models already from hubs like Hugging Face, and we can just start using, right? And so that's what I will do. So this is just inference. So to do that, we can go to our link here. So the first module for this week, transfer learning, and you can just click on this link here, code, and I've provided all the scripts already. So as you can see here, I have several scripts that I'm going to demo today. It's going to be all the IPY and B files. So I have an Albert test, a BART test, book example, Electra, entailment, Roberta. As you can see, a lot of these have in common that they are BERT models, okay? So I think the story is something, well, BERT is an acronym. It stands for, let me look this up, BERT. So I don't want to get this wrong. BERT. Bidirectional encoder representations from transformers, BERT, okay? So it's based on an LLM, like that Vaswani paper. If you've studied the GPT, is pretty much the same architecture, same beginning. It's just the last layer is going to be a little bit different. So at some later in the semester, I will get into the details of how BERT works. So today I'm just covering inference, but just be aware of that. It is pretty much the same as the GPT, the same as the transformer, but it has like a different application. And in particular, the name bidirectional encoder representations from transformers. So as we know, LLMs have produced GPTs and BERTs, right? We understand that GPTs predict the future, right? You agree with this? So I say the cat is sleeping. So essentially, it's trying to predict the next word given the previous words, right? But it can't look at words in the future. Like it can't do, the cat is sleeping on, and then it, had a dream, right? So you don't skip words in the future. You only look at the past. Whereas the bidirectional encoder representation from transformers actually predicts words by looking bidirectionally. So it looks to the past and the future. You see that? It has a different application. So it's not really a GPT, right? So ChatGPT is not based on BERT models. It's based on GPT models. All right. So, but these BERT models do have nice applications. They actually came first, I think, if I remember correctly. And I'll make this paper available. I think it's probably in the modules. I'll make this paper available a little later. I believe it was done by Meta, if I'm correct. And so they just, you have to understand how the history of this. So in 2017, we got the Attention is All You Need paper that proposed a transformer, which had an encoder and a decoder, right? Encoder and a decoder. So then Meta just said, okay, or Facebook at the time, let's remove the decoder part and let's just look at the encoder part. What can we do with that alone? Do you see that? And that, as they started thinking through that, they started to change the output layer, right? And they started to implement some functionality. So essentially, they did something like fill in the blank, right? So they would give it a sentence with a word missing randomly, and then the model was just supposed to figure out what that missing word is. Do you see that? That's why it works as a bidirectional model, because in fill in the blank, you might have words, you have a target word, and then you might have words before it and after. Do you guys see that? So that's where the name comes from. And don't worry, I'll have like a diagram later on, but for now I'm just giving you a quick introduction to what, this BERT model is. So it comes from the original Vaswani paper, right? Probably have that here. Let's go here. So if you remember, in 2017, we got the Vaswani paper, this one here, by Google. It proposed this, right? Which you guys remember, this is the transformer. It's got an encoder and a decoder, right? So then comes Google and says, okay, now this was done for translation, so it's like it would take an English word, it would encode it into an embedding, and then that embedding would go in here with, let's say, the Portuguese sentence during training, and both those two pieces of information then would go through the rest of the decoder until it started to predict the next word in Portuguese because it was translated, right? So that was the original invention, okay? And that worked really well for translation, but not for anything else. And so then Meta or Facebook comes in, and they're like, okay, this is very interesting, but very complicated, right? So let's make it simpler. So one way of simplifying things is just take the encoder part, get rid of the decoder part. Remember, the decoder part, this part is what became the GPTs, which gave us things like ChatGPT. But they looked at this part here, which is essentially the same type of neural network as this one, very similar. And so they're like, okay, in the original encoder, English goes in and an embedding comes out. But then what do we do with that embedding? Because in the context of a translation, it would just go to the decoder, right? So now they have to think, what do we do here? How do we make this useful, right? And that's where they started to think, all right, let's just do something very simple. Let's give it a sentence here, like an English sentence, and let's just use a mask, right, to randomly, like, blank out or mask one of the words. And then let's just train it to guess what that word is. Do you see that? So these are called, like masking models. But then they're saying, okay, to predict that word, we can look at, because they knew that the transformer was generating words in sequence, right? So kind of just looking at the past to generate for the future. And they're like, oh, but ours is novel in the sense that now we can look at words, if we have a target word, we can look at the words before and the words after because it's just fill in the blank. Do you guys see that? And so that's where the name bidirectional encoder representations from transformers. Got it? Okay, bidirectional. Now, why BERT? So the joke is that before all of this happened, somebody proposed an algorithm called ELMO. Yeah, which we're not going to discuss in this class because that's still not quite working. But ELMO was a little bit like this. Now you guys see Elmo, Bert. What is that from? Sesame Street, right? And so this is how AI people are nerds. So this is kind of how it went down. There was Elmo, so they're like, oh, we're going to make, a better thing. But let's think of a Sesame Street name. And they're like, let's use, I think they probably selected BERT first, and then they just figured out the acronym from it. Yeah, go ahead. Yeah, I don't remember. Elmo is, we can look it up, because Elmo it's like a stepping stone, but it wasn't that great. But it did make a breakthrough, like, it was good, but it wasn't totally based on transformers. I think it still had some RNN, so we might cover. So Elmo, yeah, so Elmo AI. Let's see. Elmo, yeah, here it is. So Elmo was embeddings from language models. That doesn't mean large language models or transformers. If you look, let's see. It was created by researchers at the Allen Institute of Artificial Intelligence and the University of Washington in 2018. So around the time of the transformer. It is a bidirectional LSTM. What is an LSTM? Who knows? Who knows what an LSTM? Do you know? Yeah, and what type of a deep learning algorithm is it? RNN, right? So it's an RNN. So RNNs, a lot of people at the time, 2016, 2017, 2018, For language tasks, they were using RNNs, right? So that was, maybe that was going to work. But there's problems with RNNs that we will discuss later. For instance, they're sequential, right? And whereas transformers are parallel. So that means that they were essentially designed for GPUs, right? So they can train much faster, and just better, right? With way more data. Whereas RNNs, they really need the previous piece of information to predict the next one. And so that's a slowdown, okay? So that's the idea. But yeah, so good question actually. So Elmo was proposed, but it used RNNs. So you can see how Facebook then, or whoever it was, they look at the transformer as I was discussing. Where's the paper? Yeah, so they were looking at the transformer, the whole thing. They're impressed by it probably, and they take the decoder part off, just look at the encoder part, and then they're like, okay, great, we can give it English sentences. We're not translating here, so what do we predict over here? So by default, as we will see later, the BERT model just produces embeddings. It's an embedding machine. If you remember the N by, what was it, 40 by 512, remember that? So you give it that, and it gives you N by 40 by 512, but it is now, we don't know what it is because it's an embedding. So their question was, how do we use this? And so the most logical first thing to do was fill in the blank. Do you guys see that? And so they trained a model for that, and they called it BERT. Any questions? And so initially that's what they did, and then from there, obviously over time, we can use it for other things. In this course, we'll cover BERTs as reward functions. So essentially, they're going to fill in. Instead of humans annotating data, we can use BERT models that can annotate data. So it's a little bit of automation in train, right? So that means that we have two models. Think about that, right? A really large GPT and a really large BERT both working together, right? So that you can make the GPT better, right? So it's a nice idea, but also a problematic idea, because before you had to train one model, right? One really large model with a lot of layers. Now you have two models, right? Because the BERT model, needs to be trained. Sometimes they need to be trained together, or sometimes you can train the BERT model first, but still, right, it's just a little bit more challenging. Because what if you don't have a good BERT model? But that's where having something like Hugging Face is really great, because Hugging Face has been around for, let's say, 10 years or so. I don't know exactly. So obviously there's a lot of BERT models that have been trained to be reward functions already. So let's say you have a task. The first thing you should do before you start training your own BERT model as a reward function is go to Hugging Face, see if someone else has done it. Maybe Meta did it, or Google, and then it might be a really good model. Do you guys see what I'm saying? So we'll explore this a little bit. So anyway, just to give you a context of the history, so there was, as I mentioned, Elmo. Meta then creates BERT, and it's a big deal, right? The BERT paper. Let's see, the BERT paper. Probably this one in 2018. You can see that it has been cited 153,000 times. That's not bad. Okay. So BERT pre-train, and this might be just another, like an older thing or a newer thing, but pre-train of deep bidirectional transformers for language understand. Oh, it was Google. Okay, so maybe it was Google. I thought it was Facebook. Let's see. Yeah, okay. So anyway, so this paper was done. That was the first in that family. And then lots of other researchers. Oh, I remember now. Roberta is actually the one that's from Meta, I think. So what happens is, okay, Google proposes BERT. Think about it, how it works, right? So right away, Facebook, which is a competitor of Google, says, okay, let's look into this. So then they take the same architecture, the same deep neural network, but with their own proprietary data, right? Because remember, that's what they bring to the game, right? What's the difference between Google and Meta essentially? They have their own proprietary data. They all have the same massive amounts of GPUs, and they all have the same talent, and they poach talent from each other, right? So essentially, what they have that's unique is their data. So then they decided, okay, let's train our own BERT. So Roberta paper. See that one? There it is. Let's see if I got this one right. So this one, is this the one from Meta? Facebook, there it is. Do you see that? Facebook AI back then. Why Roberta? Because Bert is in the thing. So this is the joke, right? So constantly they've been doing this. So there's been Bert, Albert, Roberta. If you guys came up with something, I'm sure you can find some variant of that. So you can see how it works. And this is called a robustly optimized BERT pre-trained approach. But remember, when we get to this level, right, of deep neural networks, everyone is pretty much using the same architecture. No one is reinventing the architecture. Maybe they make a few tweaks here and there. More layers possibly, right? So instead of the traditional 6 layers, blocks, as they are called, it might have 12 or whatever, because they have more GPUs. But essentially, this is how it has worked. So whenever, as we start doing the examples, you'll see me and I'll download like a BERT, an Albert, a Roberta, and so on. And just keep in mind, essentially, it's the same architecture, but the difference is better data. I've actually played with this Roberta, and I believe it's multilingual. So what I think, if I remember correctly, they use not only English, but like 100 languages. And, Russian and, Chinese and all kinds of languages. Okay. So that's kind of the idea with the BERT models. They have this kind of tradition, and then there's something like a BART, and I believe BART is a little bit different. The A actually has a meaning. They made some modifications, so it was no longer in that BERT family, like an encoder family of the LLM. Okay? All right, so yeah. So these are all great papers. In particular, the BERT paper and the Transformers paper. So we'll come back to those later. Any questions, guys, on this idea of how it works? Yeah, go ahead. Yeah. Right. That's a good question. So if you remember in 520, so the story is Google created the transformer, and the transformer it's like this, right? So this is a transformer, the original one. So if you notice, look at this carefully. There's really just one arrow here that connects them. That's it. So if you like detach, and this just means flow of a tensor from here to here. That's all it means. Like, remember, a tensor is just a matrix, right? So that a three-dimensional, like a Rubik's cube of data, right? So essentially, a tensor goes in all the layers of the deep neural network, and then you get an embedding, and then that would go in here. But this also gets another input down here. So there was like one input that goes in from the beginning and another one that comes into the blocks. And then both of those pieces of information are used to predict the next word. So what they were trying to solve is the translation problem. So what is translation? From one language to another. So the original paper talks a lot about English and Portuguese, right? So that's what they were doing. So there's an English sentence and a Portuguese sentence. So when you use it for inference, you give it the Portuguese, let's say you're translating from Portuguese to English, right? So you give it here the Portuguese sentence, goes through all these embeddings, gets processed, transformed into a final output here, and that goes in here. What goes into this is just the start of sentence symbol in inference. So during inference, you just tell it, okay, this is the beginning. Here's the Portuguese sentence. Now translate it. Do you guys see that? But during training, you do teacher forcing, right? So teacher forcing means that you don't let it predict. Instead, you use actual correct data. So that means that English comes in here and Portuguese comes in here. And then let's say 3 words of Portuguese come in, so it just predicts the 4th word. Do you guys see that? So that was the original transformer. Smart people, right, came in and said, okay, that's a really great idea, but let's break this up into 2 parts because it's actually quite complicated to, like, I'll give you my experience. When I first saw this paper, and I saw it maybe like a year and a half after it was published, I tried to understand the transformer, not knowing that there was going to be a Chat GPT in 2022. You know what I mean? So, and it was hard to comprehend both things at the same time. So actually, it's easier to understand it when you decouple them, right? So you take the encoder and you take the decoder, and then you start looking at them, and it's simpler because you don't have to worry about what's coming from here, like the sequence. Remember, they have to align and everything. So that's what happens. So this is the decoder. It's the part, you have to understand that this is the part that it takes one token here, goes through all of this, and produces the next token. And then that token is just added to the first one, and now both go in to predict the third one. And then that one gets added to the next one, and you just keep doing that. That's called an autoregressive model. So that's perfect for a GPT, especially a GPT because it just speaks one language, right? So then the encoder was meant to just take the other sentence, like in the other language, and embed it. So it's like it's taking Portuguese and it's gonna do operations, right, and semantically represent it as an embedding to have meaning that it can be used. But BERT models just decided, let's get rid of the GPT part and let's just use this. Let's see what application we can find for just this little segment here. Whereas GPTs do not use encoders, right? So you should, like ChatGPT does not use this part. It only uses this part. And that's what we cover extensively in 520, if you remember, with the baby GPT and all that. So we cover this one. Got it? Make sense? Any questions, guys? Yeah, please, go ahead. Yeah, that's another algorithm, yeah? Not this. Uh-huh. Right, you make embeddings that are retrievable. So it's like a search engine, right? And so you have like ideas or whatever it is in embeddings, and then you do kind of a search for that. Yes. Yeah. But it's not this. RAG is its own very powerful other algorithm. And I think that's covered in the Gen AI class. So I'm not gonna touch it. So ask him. All right, but yeah, so that's but it's used extensively in industry for sure, and that it's a very powerful. Yeah, but going to your point, this produces embeddings. So this is not looking at retrieving. This is just looking at you give it something like text, and then it produces a representation of it, right? And that's where I was going kind of with this story. So Google was like, okay, how do we use the encoder? What's an application of it, right? And so the first paper, the BERT, as I get into more of the details of it, you guys will see that the first things, they trained it for next sentence prediction and also for fill in the blank. Okay? And today I just plan to demo some of that as inference. Later on, we will get into more details of it. BERT is actually, we'll use it a lot, and because then we'll see how we can use it as a reward function, which is very nice. Okay? All right. So yeah, so we're focusing on this one, and we understand now where these names are coming from. So we have Bert, it's an encoder. We have Roberta, we have Albert, all kinds of things. All right, so now I think we're ready to do at least one example. Then we'll take a 10-minute break, and then we'll finish up today just going through the code, right? So that way, I'm not just like talking about ideas, but you can actually see this in action, and that'll motivate your understanding. All right, so let me close some of these. I'm not going to ask you to read all these papers. I may ask you to read the BERT paper a little bit and that LLM one. The attention is all you need again, and we'll talk about them in a future lecture. Okay. So let's close this. Yeah, and that's why we cover RNNs. Just more, it's more of a historical thing at this point. But we can use RNNs for time series. Okay, so let me close this. All right, so, pardon? Huh? That's what I just said, that, yeah. So if you ask me, what's one good application of LSTM and RNNs, right now, time series problems at it. Because as far as, language models, I mean, LLMs are much powerful. Okay? All right, so let's click on the link here. We'll do one example. So now, at least the names make sense, right? So Albert, that's one type of a BERT. Bart, like I said, it's a little bit different. Electra, I believe it's a type of a BERT model. Roberta, I talked about that one. And then we'll finish up with this idea of zero-shot classifiers. So before, you would train a classifier from scratch, right? Now you can actually just take an LLM and use it as a classifier. So I'll show you how that can be done. Okay. All right, so let's start with the first one. So I'm going to click on Albert test. Okay, so let's take a look. So this is going to be the usual pipeline that we have to follow. Remember, if you're missing any of these libraries, because I did test this a few weeks ago, all you have to do is !pip install and the name of the library if it's not there, and it should install it. All right, so I need to describe a lot of these, but let's just copy them first. All right, so notice I copied these 3 lines of code. I'm going to run it because it takes a little bit. All right, so what am I doing here? So I want to use deep learning algorithms. In fact, very deep learning algorithms. I want to use, as I've explained, an Albert, which is a type of a BERT model, which is the underlying architecture is an encoder from transformers. But this is not just architecture, because the weights are already correct. They've been, this is a pre-trained model. So that's one of the new terms that we have to learn. Pre-trained model just means something that went from nothing, right, from random values, random weights, to actually train weights. Usually this process is very expensive. Pre-training requires, today, thousands of GPUs, all the techs in the world, right, so to get a good model. So the library, this is Huggin Face's transformers. So usually I do, and there's a lot of variants of this, by the way. But here's one example. So from transformers, import Albert tokenizer and Albert model. I like this example because this is usually what we have to do. We always, whenever we want to use one of these LLMs, we need 2 variables, one for the model itself and one for the tokenizer. So the tokenizer is the thing that will map an embedding to an actual word or a subword, right? So as you will see, the model produces numbers. We have to take those things and convert them into the actual words. So we always need the tokenizer and the model. That's just how Huggin Face did it. And they usually have the same name, right? And then, I'm using pandas just for formatting here. And then there's a very convenient little module called pipeline. So remember that, here we're using the concept of encapsulation heavily, right? The underlying code, as I said, could easily be TensorFlow or PyTorch. And all the code is there, right? But what they do in their libraries is they're just encapsulating it, right? So creating an object that contains other objects, and that object contains even more objects, right? So that when we use these libraries, it's very easy for us. Okay, but the only problem with that is we're kind of like fixed in on the formats that they use, right? So especially when we want to take our data, and fine-tune a model, we have to follow their formatting. That's the only thing, and sometimes that can be, we have to get used to it. All right, so pipeline is yet another encapsulation, and it simply, as the name implies, is a pipeline. Input goes in, and then it comes out. It'll essentially has, it's verbose, so it has certain arguments where you specify the model, the tokenizer, and the function. Like, what do you want to do, right? So is it a classification problem? Are you trying to fill in the blank? Are you trying to generate text? You know what I mean? So it's just a way to make it simpler, okay? So in this example, we'll see that. So you can see that I have the green check now. All right, so now we're going to bring in our very first, very deep learning algorithms. So you can see, as I explained, whenever you see this where it doesn't have a user and the /, it's just because Hugging Face has it as one of the default models, right? So essentially, it's easy to find because you just have to provide the name. But otherwise, you have to provide the user, /, and then whatever it is that you're using. So in this case, notice how it works. From Albert tokenizer, I'm going to say dot from pre-train, and I'm going to download from the hub Albert base version 2. So the base usually means, like that's the base one that they did. Then they might have another version that is base on case, and that means it's all lowercase, right? They might, so it's, they might have different versions, like one big one small one, etc. But you can see it's, in both cases, we're using the same one from the hub, and then I have an Albert model also from pre-trained. So I'm assigning these two, and you can see it's downloading, and it finished. So I use these because they're small; they'll run quickly. Obviously, the better model I use, or the more advanced model, the longer it'll take to download, the bigger it'll be, and all that. All right, so I have my tokenizer and my model now, and that's all it takes. Think about that to get a powerful large language model. You see that? So now the advantage is we can start to solve complex problems, right? We can start to really build workflows with AI agents, all that stuff, right? Because we have these models here. And if we have a very specific task, we can take these, fine-tune them, which essentially means additional training to update the weights, nudge them. So now we just nudge the weights to be a little bit more precise on our task. But we'll learn that later. All right, so now that that's done, let's just do a few things here. All right, so you can see here I have a sentence. This is a BERT model, so obviously it handles text. So I'm going to say the cat is so sad. So I have a tokenizer here, right? So I'm going to take my tokenizer. It's going to take the text, the cat is so sad, and just create a PyTorch tensor called encoded input. Okay? Then that encoded input will go into my model, and my model will give me an output. Here, just something very basic. Okay? So let's take a look. And you can see currently it's just giving me the actual raw data. Now actually this is useful because if you're building applications, you can just take this data and fit it into your next set of layers, right? So we're going to learn that of something called the the head layers. So essentially, a lot of these models have like all the layers, like the say 50 layers, and then you would have the final layer. And those are usually called the heads because you can remove them and put another head. Do you see that for another application? You remove that one, put another head. But you always need some kind of an embedding that will feed into it. All right? And so that's what kind of what this is showing us here. All right? So for now, we're just looking at the mechanics of it. All right? And then, so you can see this output here. All right, and now we can use the pipeline example, so that essentially what the pipeline will do is that it'll handle that head. You see, so we could, of course, create the code ourselves, but the pipeline just will take care of it. That's why we specify, okay, in this case, I want a pipeline that does fill mask. All right, by selecting this fill mask, then the code, think of it as an if statement, will say, oh, okay, now I'm going to add this head, so when I get that embedding, I'm going to do this, and now I can get some text. Does that make sense? So that's the idea. And notice we're providing as a model Albert Bayes version 2. So we just create an object, which is a pipeline object called fill mask, and now all we have to do, this is just more complicated than it looks more complicated than it is. We're just invoking fill mask, which is this pipeline, and we're going to provide the cat is so, and then we have a little mask in there, and that token, it's a special token in the LLM that was unique, and so the model knows what to do with it. Whenever it sees the mask, it knows, okay, I need to fill that in, okay? So let's see how that works. So now I predict, the result, and then I just print it. All right, and here it is. So you can see that the large language model predicted cute, adorable, happy, funny, affectionate. So the cat is so cute, the cat is so adorable, the cat is so happy, and so on. Do you guys see? So that's 2018, right? So in 2018, almost 7 years ago now, right? This is, to kind of summarize, they created the transformer. They disconnected the encoder from the decoder. They decided, okay, what do we do with it? Let's fill in the blank by creating these masks, and they created this thing called the bidirectional model, and then that's a BERT. And now you can see you can see here how I'm using it. There you go. So now it's filling, the mascot is so cute, the camera is so cute for some reason, the theme is so cute, the picture is so cute, the logo is so cute. Yeah, that's what it is. Not perfect, but I think the first one is correct. Huh? It's some value here. It's definitely saying that this one is more likely than the other ones. Yeah. All right, guys. So it's 7:50. Oh yeah, go ahead. Mhm. All these numbers here, that's the embedding. But through the pipeline, though. So pipeline is handling so it's taking the Albert model so the Albert model as a raw thing just produces the embedding given the cat is so. So that's why I did this first. So we took the cat is so sad as text. Remember, tokenizer is like a dictionary, right? So think of it that way. You give it a word and it just gives you an embedding, right? So because we trained that already, and then that is fed into the model, and the model just produces another embedding. So an embedding, remember, is just like what? A vector of size 512 with numbers in it, and those correspond to IDs that correspond to words. So if I have baby, vector of 512. If I have cat, vector of 512. If I, whatever it is, right? But these are already, because this is a pre-trained model, I already have this dictionary of words to embeddings. Do you see that? So if we think about it logically, I gave it words through the tokenizer. It gave me embeddings, numbers. Then I ran that through the model. I got output. I print that out, and I get another set of numbers, right? But in this example, that's kind of like the raw model. We can't really use it that way. So a convenient way in transformers is to use this object called a pipeline. The pipeline calls in the exact same model, Albert base case, but it has this little field called fill mask. So think of it as an if statement in there that took this stuff here, think of it as a tensor, and now it attaches to it several more layers in the deep neural network. And those would be what I said called like the heads, right? So if I go back to that same paper that I had here, the Vaswani paper, and we go to the graph, right? So, text comes in, then it becomes embeddings, numbers, 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 until eventually here when we do the softmax, if you remember, and really, you see this thing called a feed forward, right? So that feed forward is the head. That layer, remember, right, will produce a vector of all the words, and it provides a probability of which one we want to choose. Do you see that? So when we were looking at the numbers, we were kind of like looking at them at this stage. And the pipeline is adding that head. Why do they do it that way? Because we could use that same BERT not just for fill in the mask, fill in the mask, but for some other application. So yes, we could code all of this, but it would be like a lot of work and really hard, right? So it's more convenient through the transformers library to just use this approach like the pipeline, and it's going to change the head for us. There's other ways of doing this, so we'll see a few other approaches later. Does that answer your question? Yeah. Sir? Um, let me see what you mean. All right, so what do you mean here? Yeah, I did change it. So you want me to change it back to the cat? The cat is so, and it's square brackets, uppercase, mask, like that, right? All right, so your question is, oh, yeah, sorry. Yeah. It's so actually this was correct though because it said it's so cute and the next thing is just exclamation marks, right? So it's like excitement. So, but let's see. Okay, so why is it positive? Is you're saying? Um, yeah, it's because of the data for sure. Right. So yeah, in the training set, I guess this was a more positive, yeah, text, that they use. So the text that they use, I guess, was more positive. If they had used 4chan to train this model, it's very likely that the outcome would have been very different. Do you guys, you guys understand? I think there was someone that actually trained an LLM with just 4chan, and then there was like a letter issued to him about it. But yeah, that's a good question. We'll actually see this a little bit of this when we come back. What you're talking about is known as bias, right? So there's bias in all these models. They try to address it. There's a lot of techniques to address bias. We've only started to discuss this now, but we'll touch on it a little bit more. All right, so it's 8:02. Let's take a 10-minute break, and let's come back at 8:12, and then we'll just continue with the examples, yeah?